Hey everybody, Mr. Perkins here. We are getting ready to do our Lab 7.1 investigation. I'm just showing you the pulley system that we're going to be using. This is just the standard setup with our physics stand and the ropes and pulleys apparatus that you guys all had in your cupboards in the classroom. I brought a set home so we could use this. So this is what we're going to be using to conduct our trials. I wanted to show you something on the bottom. As you can see, I've got a set of weights hanging from the bottom of the pulley. As you'll notice in the lab, if you look at the directions, it calls for us to use the steel weights, the big old square steel weights, but I completely forgot those in my classroom. So I had to improvise a little bit. So I used the washers and I hung them from a hanger there, and it provides some good weight for this bottom thing. This is what will amount to the output force that we're going to be lifting each time with the pulley. So as we begin, if you guys think about your data tables that you guys set up, this is data table 1, and this has the input force and the output force. I put a 6 in there. I'm going to show you how I got that number, but you're going to be working on inputting this data as soon as I show you on the trials. So I'm using what's called a force scale right here. It's got a spring inside, and you can see there's a scale of newtons there. If you flip it over, there's a scale of grams. So we're going to be using newtons today, and I'm going to be hooking this thing to a weight that we're going to be lifting, and I'm going to show you how I got those 6 newtons. So if I hook this on, and if I were to lift this up, I'll show you close there. You can see that the scale is holding right at about 6 newtons. So this is what we're going to be considering our output force. The entire thing that's hanging there has a weight of 6 newtons. And that is why I put 6 newtons as our output force. That will be the same for every trial, okay? Now, on the other side of the table, the number of supporting strings is how we're going to set up our pulley. And we're going to do arrangements of 1 string pulling the weight, lifting it, all the way up to 6, and I'll be setting those up and showing you. And then we're going to be discovering with that force scale what's the input force, meaning how much force do we need to lift this weight that we have. And of course, like I said, the weight remains as 6 newtons. So I've got my force scale set up to a string. It's hooked on, and there's a pulley. The wheel in the middle, the wheel and axle in the middle, goes all the way down, and it hooks onto the weight. So as I were to lift this, you'd see as I would pull the whole pulley, and the whole thing lifts up, as you can see. So I'm going to be using this force scale to determine with 1 string how many newtons are we using to lift up this thing. So it's going to be upside down. I'm going to try to hold it in a way that you can see it on the string. So as you can see, looking at the scale, we are sitting there at 6 newtons, which is exactly what the output force is. So in my data table, I'm going to go ahead and put 6 newtons in for the very first trial, which means that with only 1 supporting string, input force and output force equal each other. Now I'm going to set up 2 strings, and we'll see what happens. Okay, so now I have the pulley set up with 2 strings, as you can see, 2 yellow strings, and the hook is now hanging from the top support is what we call it. And it goes down and goes under the pulley there, and it's still gonna lift our weight that we're doing there. So if I were to pull this, you'll see how it still lifts the weight as I'm pulling with the pulley. But now I'm activating 2 wheels and axles for this. So I've got my little loop set up on the string. I'm going to go ahead and determine how many newtons it takes to do this. We will add this to our data chart.
Are you talking about
Here we go.
me? Are you talking about me?
Okay, so as you can see, there are 3 newtons that we are pulling right now. So I'm going to go ahead and add 3 newtons to my data chart for, oops, wrong side. 3 newtons for 2 strings. Now I'm going to set up 3 strings. Now I have the apparatus set up with 3 strings. Can you see the 3 yellow strings there? Holding it. And as I lift up the weight, I'm using the force scale to determine how many newtons I'm going to be using. So if I'm going to look at this force scale, we're sitting right at 2 newtons. So I'll go ahead and add that to my chart. 2 newtons for 3 strings. I'll set up 4 now. Now I have 4 strings set up. The pulley is set up with 4 strings. I've had to put my hook hanging from the top support again. Every even number of strings hangs from the top support. Every odd number will hook to the bottom support. So as you can see, my pulley is set up to lift the same weight, the same output force of 6 newtons. And we'll see how much input force it takes now that we're giving ourselves more mechanical advantage. So I lift, oops, I'm gonna turn this around. And I'm looking at a number, if it comes in, looks like 1.6 newtons to lift this weight. So I'm gonna put that in my next slot there, 0.6 newtons. Now I'm gonna set up 5 strings. All right, guys, now the pulley is set up with 5 strings. As you can see, I know it's kind of hard to see. You see 2 wheel and axles used on the bottom, and all 3 of them used on top. And that's gonna give us quite the mechanical advantage to be able to lift up this weight of 6 newtons. Here we go. So I'm gonna pull this. And it looks like I am looking at about 1.2 newtons. 1.2 newtons, not taking a whole lot to lift this up. So my next number will be 1.2, and then I will set up the final amount, which is 6 strings. All right, now we have our final set of trials, which is our final trial, which is 6 strings. You will see there's quite a few. All 3 wheels and axles are activated in the bottom and on the top, which is going to give us quite the mechanical advantage. Which we're looking at about 1 right there. So my number will go to 1. That'll be the final amount. Okay? We move to our second data table, and this is going to be asking us with the mechanical advantage, meaning the number of strings, because each string equals a mechanical advantage, what will it take to lift our output force, which is the same weight? It's that 6 newtons. We want to lift that 20 centimeters, which is 0.2 meters. And as you can see, as I do each particular setup with mechanical advantage, meaning the number of strings, I'm going to use the same input force. I copied this from the first data table because we don't need to reinvent the wheel and start over. We already have the numbers that we need there. Now what we're going to do is we're going to see how long it's going to take the string to pull to lift this weight a certain distance. So I don't know if you noticed there, I have a piece of tape on the physics stand and another piece of tape 20 centimeters above. I was able to measure that. I will prove to you that it is 20 centimeters. I've got my tape measure here, which is an unusual tape measure because it actually has centimeters there. So as you can see, the centimeters on the right side of the tape measure there, 1 to 20, meaning the bottom of that piece of tape to the bottom of this piece of tape is what I'm going to be lifting the whole weight. So as you can see, the bottom of that piece of tape matches up right there with the top of this. So as I lift this up, I'm going to be lifting it 20 centimeters. How long is the string going to go? Meaning you can see with 6 here, I've got quite a bit. How long is the string going to go to lift it 20 centimeters? So let me set things up and we will take some measurements. And that's what you're going to be entering in the data table, is your input distance in meters. So I'll give you the amount of in centimeters, and then of course you convert that to meters. Okay, so I've got one string set up again. We're gonna start measuring distance. We're gonna try to get that weight up 20 centimeters from tape to tape. And I'm gonna be measuring how far away this little clip that I've put on pulls away from the actual wheel. And that'll be the input distance. So here we go. If I'm to pull this weight, I'll let it kind of go and hold it from the bottom of the tape to the bottom of the tape. Hold on, actually I'll do this for a second. So as you can see, I've lifted it 20 centimeters, like I said, from tape to tape, and we're holding it in place. So Emily's going to hold this here while I measure with a tape measure. You can see from the clip to the actual pulley, it looks to be 21 centimeters, which would be 0.21 meters. 0.21 meters. That's our input distance for one string. Now I'll set up for two. Okay, so now I have two strings set up, and I'm gonna go ahead and I'm going to move this. I'm gonna pull this up 20 centimeters again. So there goes the weight, 20 centimeters, and I'm gonna hold this in place. I'm gonna hand the camera to Emily so she can hold it in place while I measure. So now once again, I'm measuring from the peg or the little pin that's on the string all the way up to where where it meets the wheel and axle. So obviously this one's a little bit longer. I'll go longer with my tape measure. So as you can see, we are measuring at, looks like this is 41 centimeters when we use two strings. 41 centimeters, which would be our input distance to lift the weight 20 centimeters. The string let out 41 centimeters, so 0.41 is what that converts to in meters. Now I'm gonna set up for three strings. Okay, now I'm set up with three strings once again, like we set up before, and there's my peg right there. So I'm gonna go ahead and lift this weight 20 centimeters from tape to tape, like before. I'll have Emily video after that, and we will see how long the string goes, because it's coming out pretty far. So I'm gonna hold this string. I gotta put this, yeah, Emily's helping me there, thank you. So we're gonna hold it right there. So I'll go ahead and hand the phone to her, or the video to her. And then so now I'm gonna go from peg all the way up to, didn't go far enough. Yeah. From peg all the way up to the, yep, right there. Perfect, thank you. So from peg all the way up to the pulley itself is 62 centimeters. 62 centimeters after three strings. So 62 centimeters, I would put that right there, and that would be a 0.62 as our data for three strings, as you can see. So now we set up four strings. All right, now we're looking at four strings here. I've got my peg up and ready to go. Four strings, both wheels are activated in the bottom, two wheels are activated on top. It's gonna get pretty long. So I'm gonna go ahead and hold this out. I have to scoot this back just a little bit. We're gonna hold it out. We're gonna lift this 20 centimeters, which puts it right there. So we'll go ahead and so we'll hold that in place. I'm gonna use my tape measure. I'm gonna go ahead and measure from the wheel all the way down to the peg we are looking at 83 centimeters. 83, as you can see on the tape measure there. So we're gonna add 83 to our data chart. 0.83 meters, because that's 83 centimeters. You're starting to notice what happens. Roughly, there's a bit of a trend going on here. As we increase the mechanical advantage by 1, you see what happens to the distance the string goes. I'll set up 5, we'll do 5, and then we'll do 6, and that'll be all the data that we collect. Okay, so now I've got 5 strings set up. You see 2 wheels and axle are on the bottom, all 3 on top. So I've got my peg, my little pin ready to go. So as I pull this up 20 centimeters, and we get that to the tape right about there. Go ahead and hold that in place right there. And then Emily will video that while I measure. This one's gonna be even longer. Our distance goes from pulley all the way down to the peg. We're looking at about 100, and we'll fudge it and say about 102 centimeters. 102 centimeters, AKA 1.2 meters. So I'll go ahead and put that right there. 1.2 is, 1.02 for 102 centimeters. So I'm gonna set up for 6 strings. That'll be our last piece of data that we need the physics stand for. All right, so as you can see now, we have our 6 strings activated, all 3 wheels and axle on the top, all 3 on the bottom. I've got my pin in place right there. I'm gonna go ahead and pull this string out. We're gonna see how long it goes to get this thing, the weight up 20 centimeters. It's gonna be pretty long. So right about there. Right about there is good. Yep. Okay. So as you can see, this takes the string right to the counter. And so Emily is holding that in place. So I can do this long measurement. So from the pulley all the way down, let's see if I can get this to hold in place. We're looking at 126 centimeters. 126, we'll say 125. 125 centimeters is right where it's at for the final one, which would be the same as 1.25 meters. 1.25 meters. So, and there's your data. There's your input distance for the pulley. So mechanical advantage is basically the number of strings. The output force remains the same weight that we used before. The distance that we wanted to pull it was our 20 centimeters from tape to tape. So the input force, if I were to use the force scale, would be the same as our first experiment we did. And there's our distance in meters on the string from the top of the pulley to wherever that peg ends or that pin ends up for the string. So that gives us the information we need to go to our final data chart, which is going to be asking us to determine the work, the output work and the input work. So as we think about it, the formula for work, W equals F times D, force times distance. So if I know my force, let's go back up. If I know my force is 6 for output, meaning the weight, and the distance that I made it travel was 20 centimeters or 0.2 meters every time, then my output work is going to be the same every time. And you would take W equals F divided by D, or 6 divided by 0.2. And that'll give you the amount of work that was generated as we lifted this weight 20 centimeters. Now the input work, on the other hand, is a little different, because if I go back up to my previous one, I've got my different forces. There's my input force. So W equals F times D. Did I say F divided by D? I'm sorry. 6 times 0.2. So here is 6 times 0.2, or 0.21. The numbers should be rather identical, because with one string, you have really no mechanical advantage, or mechanical advantage of 1, okay? So then I move down, W equals F times D. There's my F, there's my D. So as you can see, that's how we're going to be able to determine the work in joules. So you don't have to put a letter down because you've already written joules right there, all right? So you need to determine the output work and the input work in order to complete this data. As for the questions in the lab, I will be instructing you with some directions in classroom. So that concludes the data portion of this lab. Good luck, guys, as you watch this video and enter the correct data into your data charts. I'll talk to you later.